Today I'll be talking about embracing uncertainty in numerical models. As a numerical model, I always like to start off my talk by saying all models are wrong. This is a famous quote from George Box. He's a statistician. It boils down to all models are approximations. They're not reality. So essentially, they're all wrong. Since I make my money as a modeler, I should point out that, but some are useful. So my thesis is one of the major limitations of a numerical model is the input parameter uncertainty, but this can be mitigated by applying reasonable ranges or distributions for input parameter values. You can then create multiple realizations or versions of your model. You can use that in various ways, for instance, to quantify the impact of parameter variation on whatever you're interested in finding out with your model, which I've called the metric of interest here. So for instance, in Southern Ontario, maybe you're looking at one reservoir and you've got just one measurement of geomechanical properties for the A2 anhydrite cap rock, for instance. But over many pools, you might have many measurements. So this type of information you could then use to estimate a reasonable distribution of properties for that particular unit and other units. And you can then use this distribution and you can sample from this distribution to create multiple realizations or versions of reality, which you can then run in your model and use it to quantify the relative importance of various parameters. Maybe you'll find out that A2 anhydrite properties are not terribly important to whatever you're looking at, but you don't know that in advance. And so in a way, it helps you to reduce your uncertainty and focus on what's important. So I'm going to look at two examples. One is underground gas storage in a pinnacle reef, which, as you all know, there's lots of it in Southern Ontario. This was a project where we did more like a deterministic sensitivity analysis. It wasn't probabilistic in this sense that I was talking about previously. Our metric of interest here is the maximum percent fracture gradient. The second example is from our work in radioactive waste. This was a probabilistic type safety assessment. And so I'm just showing this as an example a little bit, I guess, to stimulate some interest in what we could do by taking these ideas and bringing them over to underground gas storage. And here we're looking at contaminant flux to a hypothetical well, very hypothetical. So delta pressuring, very, very quickly. So this is our first example. The operators wish to increase maximum operating pressure. They want to do this to increase the capacity and deliverability, potentially, subject to limitations in surface infrastructure. And our role here was to assess the safety and regulatory compliance of increasing the maximum operating pressure. Very quickly over the regulations. So CSA Z341 is the applicable standard, or I guess it's in Ontario, that's what the regulator requires the operators to follow. And it allows delta pressuring, which means increasing the pressure beyond the discovery pressure of a natural gas reservoir, up to 80% of the fracture gradient. And the fracture gradient is defined in the regulation or in the standard as the pressure gradient that, when applied to subsurface formations, causes the formations to fracture physically, which we would interpret as you can't increase your pressure beyond 80% of the minimum principal stress. But of course, the fracture gradient changes as the pressure is cycled in the pool. The effective stress is influenced by changes in pore pressure and changes in confining pressure, or confining stress, mechanical. So when the pool pressure is high, confining stress in the cap rock is reduced. This is just a cartoon here, but you get the idea. And so we developed numerical models to assess stress changes induced by pressure cycling. And the workflow we use, first of all, we did a flow model looking at pressure history in the pool and potentially gas migration, depending on the permeability in the cap rock or other features. So we're looking at flow over multiple years of operation. We then take that information and feed it into a geomechanical model, which is looking then at the stress changes during reservoir pressure cycling. Finally, we combine the results of those two models and calculate the maximum percent fracture gradient. So this is the reservoir we've chosen for our example here. It's a cross-section through the reservoir. You can see a pinnacle reef formation in the center, and there are the A2 anhydrite, which I talked about before, and A2 shale, A2 carbonate cap rocks above the pool. This is the same pool. Now it's a little bit of 3D, just a nice pretty picture for everybody. This is the A1 carbonate, top of the A1 carbonate. This pinches out against the sides of the pinnacle reef flanks and is thought to provide secondary storage in a dolomitized zone adjacent to the reef, although I'm sure the geologists who were speaking earlier today might have a different opinion on that. Maybe it's rubble or some sort of thing. I'm not a geologist. I'm a numerical modeler. This is the top of the A2 carbonate, which comprises part of the caprock formation. Finally, here's the B salt. So it gives you a bit of an idea. Obviously, there's lots of layers in between those, but anyway, you can get a sense of the overall 3D structure. So we wanted to do a sensitivity analysis with our model of this pool. The goal of the sensitivity analysis is to study how uncertainty in model input parameters affects the variability of a given model output. So what we did was we set up what we call a base case model. That model represents our best estimate of the likely subsurface conditions. So if we were only going to do one model, that would be it. That's what we think is most likely to be true, but we're not 100% certain. So then we varied the input parameters to this base case model in a series of 36 sensitivity cases, which are all listed off here. It's not important to go through all those, but the parameters we focused on were caprock elastic properties, reef or reservoir elastic properties, caprock gas permeability, minimum principal stress, and of course storage pressure. We varied to look at that as well. That's the primary goal of most of this work. It's a little video showing gas moving around in the pool as we cycle pressures. So there we go. The inset plot up in the corner shows the measured and modeled pressure history, so there's a nice match there. To get that fit, we did require heterogeneity within the pool, within the reservoir, and that's also apparent in the pressure gradients across the reservoir during injection and production, which are a function of both heterogeneity and the location of the injection wells. You can see the observation well is right here. So this is the same plot, just zoomed up a little bit so you can see it closer, a nice match. We ran scenarios, obviously, where we increased the pressure. So we just took this same historical pressure data and we increased the injection and extraction rates in order to achieve a maximum delta pressure, in this case for the green line, 0.76. So it started at 0.7, it was current pressure. 0.76 is something that is of interest. And then we also ran a scenario in the blue, that's at 0.8 psi per foot. So then output from this flow model that we were developing was used as input to the geomechanical model to assess stress changes in the caprock. Here's our base case model. Just a visualization showing caprock elements. These are the elements here with the highest percent fracture gradient in the A2 anhydrite, sort of shown here in kind of a profile. I think it's easier to see in a cross section. So this is the same model. We're just looking at now minimum principal stress. The feature of interest here is just to see how we're getting a reduction in compressive stress in the caprock directly above the pool. And that's what we're looking for. This is the effective stress, so now we're including the effect of pore pressure. And finally, this is the maximum percent fracture gradient. The maxima occur in the upper part of the reservoir and in the A2 anhydrite caprock. I guess I should point out, we've got some bright red and orange. It looks pretty extreme, but the value we're at here, our maximum is only 60.3%. So we're well within the regulatory limits here, because we're allowed to go up to 80%. So there seems to be lots of space for adding additional gas. Now this is the exact same data, I've just plotted it up. Now we're maxing out at 80. I think this better reflects the current situation. So let's look at a few scenarios. I'm not going to go through all 36. Looking at what happens if we change different things. So this is just the same base case model. Now we're at 0.8 instead of 0.7 psi per foot. Our maximum gradient goes to 70% roughly. If we reduce the minimum principal stress by 5%, we get a further increase. Now we're at 73, starting to get a little bit higher. Now in this case, we increase the compressibility of the reservoir, and we decrease the compressibility of the cap rock. And here we finally find a scenario where we slightly exceed the regulatory criterion. However, I think this should be considered an extreme end member scenario, kind of with a low probability. And this is kind of a quick summary of all the scenarios. You can see that at 0.7, we range between 60 and 75% just by changing various parameters within some limits. And if you go up to 0.8 psi per foot, the maximum is at 82, but they range between 70 and 82. So finally, in summary of this first example, the majority of cases didn't exceed 80%. Despite data scarcity, running this sensitivity analysis allowed us to conclude that increasing the maximum operating pressure to 0.76 psi per foot is safe and within the limits of prescribed in the regulation. And it allows us to prioritize future field data collection efforts for those parameters which have the greatest impact on fracture gradients. But I guess what I want to talk about a bit is how do we automate this process perhaps to improve statistical rigor. And so now I want to look at another example. This is a radioactive waste. This is contaminant transport. This is a case study we did for the Nuclear Waste Management Organization, and this is a conceptual repository in a hypothetical low permeability faulted crystalline rock geosphere. And the dose pathway is groundwater transport from defective containers, which, well, those are little containers in a tunnel, through the engineered barrier system, bentonite clay and things like that, then eventually through the intact and faulted geosphere, reaching a hypothetical well. It's all very hypothetical. So hydraulic conductivity, or permeability, unfortunately, this is all in funny units of meters per second, but controls contaminant transport. But below a certain threshold, it is no longer important, because diffusion, which is just transport along chemical gradients, becomes the dominant process. And that's where you want to be in a rad waste repository. You want to be in that diffusion-dominated regime, because it's much, much slower transport. So the question is, how low do we need to go in choosing a site? And also, if you want to choose a site, you have to measure down to those levels. So how low do we need to measure, really? And that has a big effect on price of those field programs. So we used a probabilistic framework to randomly sample input parameters, in this case diffusivity, dispersivity, and hydraulic conductivity or permeability. And for each sampled set, we ran the model and we assessed the key metric, which is the concentration breakthrough in a hypothetical drinking water well. And so this 3 axes here show those 3 parameters, and there was 100 different simulations run here with a very broad range of output. So these are breakthrough curves, these are transport to the well, and the bottom axis is time. So you can see there's a big, big range in output, and there's a strong correlation between peak transport time and maximum transport rates. But to better understand this result, we took a look at some correlations. So we started looking at correlations between input parameters and output metrics. Clearly the hydraulic conductivity, which is the top chart there, seems to be the dominant parameter. But if we separate outputs into windows of sort of equal hydraulic conductivity chunks or gradients, so the story becomes a little bit more interesting. So below this 10 to the negative 12 here, which is 0.1, it's 100 nanodarcy. So below that level, it's really diffusion dominated. And then we get into this regime where we're shifting from diffusion into advection or flow-dominated transport, and over here we're clearly in flow-dominated area. So I think that tells us that we can conclude that for this geological setting, we have to measure permeability down to 100 nanodarcy. This is another example showing a comparison of sensitivity to host rock permeability and an engineered barrier properties on this side. If we just focus on the gray lines, you can see that there's a lot more sensitivity to the host rock parameters than there is to this engineered system. So that kind of tells you that selection of a good site is a lot more important than the engineering of the sealing system, which I hate to say as an engineer, but anyway, that's what it tells us. So in conclusion, we can't make a perfect model. There are always approximations, but we can constrain the variability of model inputs. And if we recognize uncertainty, when building models, we can better understand the confidence we can have in the model, the range of possibilities. We can direct new geological field characterization as efficiently as possible. And finally, perhaps we can integrate these probabilistic model outputs into risk assessment frameworks down the road sometime. Another quote from George Box: since all models are wrong, the scientists must be alert to what is importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad. So I think this type of probabilistic modeling lets you focus on the tigers and ignore the mice. And thank you.